Okay, in this video, we are going to look at a past year question from Summer 17 paper 41. It's a pretty standard magnetic fields question. Here we have an electron with charge negative Q and mass M accelerated from rest. So this from rest is a pretty important information, meaning it means that the kinetic energy, the initial kinetic energy is zero lah. Okay, so in a vacuum through a potential difference. Sure. The electron enters the region of uniform magnetic field. So this gray square is a uniform magnetic field of magnetic flux density B. Okay. So this is part of the electron. Just a quick reminder that the electron is a negative charge. So maybe I'll just put negative E. All right. The direction of the uniform magnetic field is into the plane of the paper. So it's headed into the plane of the paper. There. Meaning the magnetic field is going in. So in this particular example, I won't provide the top view lah. Okay, so practice and learn to use your left hand to confirm the direction of force. Okay, so right now, my thumb is the direction of force. My pointing finger is the direction. Again, my image is flipped. I guess I should be using my right hand then. Okay, so my pointing finger is the direction of magnetic field. My middle finger is current, FBI. So if you use FBI and you put it inside, you will notice that your finger must be pointing into, because the magnetic field is into the plane of the paper. Your middle finger must go against the direction of the electron flow. So right now my middle finger follow the direction of electron. But it shouldn't be, right, because direction of electron is opposite to direction of current. So it should be like that. So your hand will be something like this. I'm not sure if you can see, something like this. Your thumb is going downwards. That's why the electric force is down. Sorry, the magnetic force is down. So a lot of times, right, when it comes to this kind of question, even if it's pretty obvious that the magnetic force is pointing downwards because the pathway is down, but it's also better to just confirm with yourself lah, to make sure, so your brain feels more satisfied. So A, explain why this part inside the magnetic field is the arc of the circle. So if you've watched the video that you have, you will notice that the direction of FB is always perpendicular to the direction of velocity. So wherever the particle is, the FB will change. This one is 90 degrees. Okay, so that will be the first point that you will say. That is the magnetic field. The magnetic force is always normal, perpendicular, or normal to the direction of velocity. That will be the first mark. Okay, magnetic field or magnetic force, sorry, not magnetic field, please use magnetic force. Magnetic force is perpendicular to the direction of velocity. Dun, dun, dun. Second point. For you to maintain circular motion, this magnetic force have to be constant. Is it the magnetic force is constant, and the speed or the magnitude of velocity, speed of electron, is constant. So if you have a bunch of constant stuff, right? For example, this is uniform circular motion. So think about your chapter 7 or in your A2. So when V is constant and this V, the velocity here, this V is constant, this means that wherever the particle is, so let's say this is the tangential velocity, and this is the, hang on, my drawing is a bit off. This is the tangential velocity. Okay, this FB is always 90 degrees to the tangent. Let me fix the drawing a bit. Personal preference. So the direction of FB will be like this, 90 degrees. Okay, So of course, if you have a ruler, you can draw better lah. So this FB and V is always 90 degrees as it travels. All right. So this is why the magnetic force is constant. Because if the magnetic force is being greater and greater, then it will spiral inwards. So there's more pulling towards the center. If you are turning faster and faster, you will spiral outwards because you need more centripetal force. So we need both magnetic force and speed to be constant. Okay, so hence, we can say that the magnetic force provides the necessary centripetal force. Okay, magnetic force provides centripetal force. So this kind of question, right, when they ask you to explain, you talk about force. Talk about F, B, magnetic force, on the electron. So magnetic force on the electron is perpendicular to the direction of velocity of the electron. Magnetic force is constant, magnitude is constant, so is the speed of the electron. Because of this, the magnetic force provides the centripetal force. All right, so part B, show that the magnitude of momentum of the electron as it enters the magnetic field is given by this value. Okay, so I think if we want to find momentum, it might be a bit strange. Miss, why talk about momentum one? Notes never see momentum before also. So I guess if don't know what to do, we write the equation for momentum law. P is equal to mass times velocity. And I stare at this equation. There is mass, but there's no velocity. Okay, just in case you are lost. This V is velocity. Okay, so there is no velocity here. And this V is potential difference. Is it? Let's see. Let's check. Normally they will tell you in the question one. Potential difference V. Okay. So this V is your potential difference, and I'm going to put it down here. So basically, I need to relate V and this V and this V lah. Okay, so step 1. The reason why we have velocity in the first place is because the potential difference accelerates the electron. So perhaps the electron will have to be... So what they will do is, before the electron enters the magnetic field, let's say the magnetic field is here lah. I'm just going to draw a box here to represent the magnetic field. To allow it to have a certain speed when it's accelerated from rest, right? What we'll do is we'll just put some plate here that is not drawn, okay? And then let's say the electron here, the V is equal to 0. And of course here, maybe I will put another plate here, and then here is grounded lah. So the potential difference here is V. Let's say here is positive V. So the electron will be attracted to the positive plate. So here V equal to 0. By the time it enters the magnetic field, there will be a V here. So I guess we need to find this V lah. But if you just look at this parallel plate, which is a very reminiscent to AS situation, what we're trying to say is work done by the electric field or by the potential difference is used to accelerate the electron. So I'll write that down first. Work done by the electric field is equal to the change in kinetic energy of the electron. To that, I can write the well-beloved equation Q times V. But in this case, it's electric field. I mean, they use Q lah. Then you follow lo. Q is the charge. You can obviously use 1E as well because this is an electron. But follow the question. So this kinetic energy will be half mv squared minus 0 because it starts from rest. Okay, so this Ke here is 0. And this Ke here is half mv squared. So I guess we will rearrange this and I will get a value of V. So our purpose here is to substitute this V, velocity. All right, so the velocity is here. So I'm going to substitute this one by doing some rearranging. So I'll get 2qv over m square root. Okay, not a very nice term, but don't worry, we can soldier on. So step 2, you can then say hence momentum is mv. So this will be m times square root of 2 qv over m. In order to get that expression, I need to bring this m into the third form or into the square root. So what I'll do is I will change this m into m square so that I didn't change my value. And then here will be 2 qv over m. So obviously the m square and m will simplify and cancel out. And what you have left is square root of 2, let's copy the answer on top, 2 mqv. Yeah. All right, because the m and m will cancel. So proven. It's not very long. They are just testing and see whether you can relate the work done by electric field, QV, through this one. And also draw the information from here. Potential difference is V. So this is your delta V. Okay. Please don't confuse lowercase v. I tend to write lowercase v like this as velocity, and uppercase v, I write uppercase v like this so that they look different. Like this, as potential difference. Okay, so this is part B. Let's move on to part C. In part C, you are given the potential difference and the radius of the circular arc. And then you are asked to determine the magnetic flux density B. Okay, I guess you could be thinking, can I use B? I would prefer not to do so because I can think of a very straightforward way. Magnetic force is the one that causes it to move in a circular arc. So magnetic force provides centripetal force. For a moving charge, the magnetic force will be BQV. Means need to sign theta. No need. The theta is 90 degrees because the magnetic field is going into the paper. If you stare at this one, the magnetic field is going into the paper, but the particle is traveling across the paper. So if your pen is traveling across your paper, your pen is perpendicular to lines that are pointing into the paper. It's already 90 degrees. All right. So here we have FB is equal to FC. So we can use BQV is equal to, I guess, MV square over R. These are the same velocity, so we can cancel them. Okay, and we are looking for B, so I will rearrange. I will have MV over QR. Please start from here. Don't memorize this equation, although you tend to see it many times. Because got mark 1. The mark is here. This point here is 1 mark. So if you didn't write this, you straight away jump to this, then cannot at all. Or you're up to the mercy of the examiner, which I kind of prefer that you don't become like this. Okay, so you want to determine the magnetic flux density. Then you notice, hey, wait a minute, this MV is equal to momentum. Sure, because you can actually go and see that we don't have the value of the, what do we not have? We don't have the value of V, velocity of the particle. Do we? Let's trace. Do we have value of V here? Do they give value of V? Nope. You are not given the value of velocity. But so this is why they want you to use B. So this is kind of like trying to help you to recall that momentum is equal to this expression. Right, so what I'll do is I will substitute my MV into the expression that is already derived in part B. So our momentum just now was square root of 2. Hang on, let me copy again. 2 mqv. Okay. Over QR. This V is potential difference. My bad. Let me make it more clear. There we go. So now do we have all these numbers? We do. So this will be square root of 2. Miss got mass meh? You guys, it's an electron. So if it's an electron, this will be 9.11 times 10 to the power of negative 31. Okay, let's continue the square root bracket. I guess you could write to the power of half. Q is charge of 1 electron, so 1.6 times 10 to the power of negative 19. Potential difference is 120. All right. Ding, ding. Well, you don't simply cancel lah. Okay, so if you just want to key the whole thing into your calculator, that is also okay. If you want to bring this Q into the surd form and simplify, also okay. I'm running out of space, so I shall not do that. Radius is 7.4, so 7.4 cm times 10 to the power of negative 2. Yes. So I'm going to press my calculator now. BRB. Okay, so after pressing my good friend Casio, the calculator, I got 4.995 times 10 to the power of negative 4. So I guess changing it to 2SF will be 5.0 times 10 to the power of negative 4. My friends, you change it to 2SF. The idea of magnetic flux density, right, is that this number always have to be quite small. Millitesla or something of that order. If your answer is too big or too small, it means something is wrong. All right, so please double check your substitution. A brief reminder that the mass of the electron 9.11 and the charge of the electron 1.6 and its exponents are available in page 2 of your exam booklet. So don't forget to flip to the front for constants if you don't remember them. Okay, so where are the 3 marks? 1 mark is for this writing, this equation, and substituting this. The other mark is the substitution here. And the final mark is the answer. Okay. So that is this question. Let's look at part D. In part D, the potential difference V is increased. Magnetic flux density B remains unchanged. So B remains unchanged and potential difference is increased. So let's do a bit of a back of a napkin calculation. I write down the equation first. The equation that we have is this one. B is equal to mv over qr, which also happens to be square root of 2 mqv. Ding, ding, mqv. Do it slowly, no rush, over qr. Okay, so just a reminder again. So this is how you kind of like keep catching yourself in case you are the type where easily confused. This is the speed of the particle. This is the potential difference. Okay, so it says potential difference increase. So this V increase. Magnetic flux density remains the same. So this B is constant. I'm just gonna write that here. This one is constant. By reference to momentum of the electron. Okay, so that means I'm going to use B is equal to, using the momentum, P over QR. Explain the effect of this increase on R. So we want to explain how, when V increases, how would it affect R? Will R increase or decrease? Okay, so I think the first order of business, right, is to remember that the momentum in part B is equal to 2 mqv. Okay, so as the potential difference increase, what happens to the momentum? Momentum also increase. So you stare at this equation. When momentum increase, to keep B constant, R should, pause, think, what do you think? If the numerator is bigger, then the denominator must also follow to become bigger to not change. If writing like this, you cannot, because you just struggle with writing it this way. What you could do, another option, is writing it this way. BQR. Okay, so what are constants? B and Q, constant. If B and Q are constant, then I can say the momentum P is proportional to R. So since I know P increase, R will also increase. Okay, so those are the 2 points. So the first thing I would say is to relate it with momentum first, because they're asking you to refer to momentum. So definitely here got 1 mark 1. So right here, larger potential difference causes a greater momentum of the electron. First point. Okay. Then explain how it affects R. So because there's a larger momentum, hence, since P is equal to, I guess you could use BQR. There, P is BQR. Or any equation, B is P over QR. Okay. Hence, since P is equal to BQR, the radius of the circular part R increases. So those are the 2 marks. So I think the takeaway here is sometimes the question can be tricky. They might suddenly come out with a random term like momentum. Okay, lor. So don't forget, like, very basic things. If they're tricky on familiar ground. It's like you already level up to level 10 and suddenly you see terrain from level 2. Don't worry, you got this. All right. So here, what we had was they are trying to guide you by first giving you momentum. Okay, so what you need to think about is how do I relate velocity to potential difference, which is work done. Miss, what if I totally forget this or cannot recall this because my brain is stuck in magnet? Never mind. Use their equation. Use this expression, P is equal to square root of 2mqv. Just remember V is potential difference and substitute into here. Just remember momentum is mv though. Okay, and then this one is just a basic calculation, right? The final part, if you want to relate potential difference to magnetic flux density, especially in part D, when we want to relate the potential difference to the change in radius and keeping the other variable constant. So I guess the challenge here is that you have too many variables: mass, velocity, potential difference, momentum, radius of the circular part, magnetic flux density. So it's important to take your time to figure out which are constants, which are increasing, and how are they interrelated to each other using the equation at hand. All right. And normally when it's an explain question, the question will try to guide your explanation or what to write. So it says reference to momentum. Definitely you need to have a relevant statement about momentum that relates to what happens when the potential difference increase. Potential difference increase, momentum increase. The particle will travel faster, right? So since P is equal to BQR, so based on what evidence you have, radius will increase. All right, so that's it for the question. If you find this helpful, please do try more other questions, and good luck in your studies. Like, subscribe, you know what to do. I'll see you in the next one. Bye-bye.